Advent of Code, day 11. I'm gonna read through this and then get back to you. Okay, so we're doing a similar grid recursive search thing to what we had a couple of days ago. It should be pretty easy, so let's just get into it. Ooh. Hold on, let me fix my Lua config. Okay, now my Vim config is fixed. Let's do target util release util scaffold. Year is 21, day is 11. Okie dokie. And now let's go into that 21 day 11. And let's start figuring out our input. So we are going to need to use ND array2, same way we did last time, which means we'll also need array1 to, get the whole thing, and we will need is our final grid 10 by 10? It is. Okay, nice. We will need array view mute 2 as well for some of our functions. Okay, and then for our input here, we're going to say our grid is array2 u8 because they don't need to be big. And then we're going to pass this, and so we're going to need what do we need? We're going to need bytes complete take. We're going to need character complete line ending and u8. We're going to need combinator map res, and we're going to need combinator map. Let's combine map and map res. Okay, and so then we want to say let octopus value equal. That is our made-up theming for this, isn't it? We're octopi. We are octopi. Is take one usize and then u8, and then we'll say let row is equal to. We also need many1 multi many1. Row is equal to many1 octopus value, and then we will say let rows is equal to separated list1, which we also need, but let's put that in here, multi separated list1 of row, and line ending is the separator. And then we will say let grid equal map result rows into, and this is going to be a vec of x, so we need to do rows dot into iter dot flatten dot collect as an array1 dot into shape grid shape usize is a 10 by 10. We're going to hard code that for now. Grid shape. Yep, and then we're going to say let parser is equal to map grid passed input grid parser.parse input. We also need to bring in parser and get rid of that semicolon. Missing generics for type. Let's have a look at that in the terminal. Right, yes, of course, that makes sense. Array1 of u8. Just whatever you've got, which it knows must be u8. Okay, so now if we debug input.grid, and let's set up our test input. Let input equal, you all know the drill by now. We're gonna do this .trim, and then we put our input back here left shifted. Here's our test input. And then we have got task assert task, pass task 1, input, and then what do they actually want as an output? What they actually want is 1656. Okay, and this is running for 100 steps. Okay, let's make our lives really simple. Let's just do a increment. Let's just have an increment count function that just does this entire task. So increment count is going to take a view of an and mute array view mute to u8, and it's going to need to have a counter, which is going to be an and mute u size. And the reason we're doing it like this is this is going to do our recursion. It's going to count each flash basically. So yeah, if we increment and we go greater than 10, then we want to set to 0 and flash out to our neighbors, which is how you get this behavior happening. And if our neighbors, yeah, okay, so here, and we also need a target of u size. Nice. Okay, so this is going to be our basic increment count function. So what we do is we say let target cell equal target octopus is equal to view.getMute target. And if there's none there, then we're fine. We just want to return. This would be a great place for a let else guard, but given that those aren't a thing yet, we'll say if let sum v equals this, v else return. Eventually let else guards will be a thing. So now we have our target octopus, which is an unmute u8, and we can do target octopus plus equals 1. If target octopus is greater than 10, we need to flash, otherwise we will just return. And so when we flash, we say target octopus. Now hold on, backflashing isn't a thing. Can flash at most once per step. So what we actually want to do is do our recursive step here to prevent backflashing. So if it's greater than 10, then we're going to flash out to our neighbors, and they will be simply what we really need is like a flash tracker. Which I guess we can just encode in our recursive state. If flash is not, if we have not yet flashed, then flash is true. We're going to flash, and then we are going to recurse out. And the way we will do that is by just calling this on all of our neighboring cells. So let's actually say our target here is going to be target at CYCX. That should be legal syntax. And this is target flashed. Yep, okay, so now we have CUI and CX available. So now what we can do is we can say, we have to guard a few of these. So we have to say, if you know how we can do this? We can just say, well, if we call on ourselves, it's fine. Nothing's going to happen because we have already flashed. We won't recurse again. We would be double incrementing though, but that shouldn't matter. It shouldn't matter how high we get if we're flashing anyway. So I think that's fine. So let's actually use slice syntax here. And let's say we're gonna build a slice from, this is where ND-array slice Rust. I need to look up how the slice macro works. I can never remember. It's just called S, really unhelpfully, so it'll be down in macros. Macro. S, okay, slice. How on earth do you work? It's by axis, okay. So we would like to look at the slice from cy minus 1, cy saturating sub 1 to cy plus 1, but we want to limit it to max. So let's just say grid shape is a single use size for now. We can refer to that, and here we can just say grid shape. So we need to go from cy minus 1 up to cy plus 1, but we want to saturate, so we want to say cy plus 1 dot min grid shape minus 1. So if it's 8, we'll go to 9. If it's 9, this left side will go to 10. The right side will still be 9. Can't go out of bounds. So that is our first one. And then for our second axis, we want the same, but we want it for CX. Okay. So that is our full slice bounds. So what I'm going to do is I'm going to say view.sliceMute of this, and we'll say this is our region. And we'll say for place in region. We're actually better off just doing this as doing this hard coded, because we don't want to have local coordinates. So let's actually just say for y in this range here. Nope. Control visual. For y in this range here. For x in this range here. Increment count view yx slash counter. So that's going to flash all our neighbors, and then what we're going to do is we're going to say if we were greater than 10, after once we have flashed all of our neighbors and they flashed all of their neighbors and this whole thing has spiraled out, we want to say counter plus equals 1, and we want to say target octopus equals 0. So after we do that whole recursive spiral out to sort of hit everything, we're going to recurse our way back in. Count of our review is mutable. We don't need target. Okay, it's because target octopus has. Okay, here let's drop target. Oh, that's really awkward. We are just gonna do it here though. We're gonna say here we'll just rebind target octopus. And now the lifetime can be shortened. We can do this here like that. we can do this here like this. You know, there's got to be a better way of doing this. What's the actual issue? It doesn't like that. Oh, okay. Well, it's suddenly happy with this, so I'm not going to worry about it, and we'll see if it has a problem. Now let's check. This is going to fail, but we have our grid. We do have our grid. Good. Now let's use this increment count. So what we want to do is and how many times do we want to do this? We want to do it after 100 steps. 4 in 100. So we're going to say let grid equals input.grid.clone. Let grid equals grid.view mute to get our mutable view. Mute grid. Okay, and then we're going to return a usize from the end of this, and we're going to say let mute count equals 0 and start here. And we're going to say let mute flashes, because we need this sort of flash storage going on, is equal to array2 from element grid shape false. And then this here is flashes view. Yep, okay, and then down here we're going to just say okay count. Okay, and now in here, for just do this 100 times, increment count, we want to do it on our grid. We want to, so here is where we actually go, we want to do every single position. So we want to say for y in 0 to grid shape, for x in 0 to grid shape. Now we only actually want to run flashes at the end, don't we? I'm thinking about it. We kind of want two functions, increment, that's going to run over everything. Let's see if it works like this, but it might need to break this into two functions. So yx flashes and counter. Count. Our test failed. We only found 1,000, but there were 1,006. There were a lot more than 1,000 to find. Okay, so let's have a look at just that first step on this one. Let's have a look at that first step on our test. Was to go from here to here, no flashes. Okay, and then after step 2, we should have some flashes. So let's do if I01 is equal to 1, so it's an I. Then here we want to debug the grid. Okay, so this gives some wrong values, and it's probably because we're over incrementing things. Actually, that would cause too many flashes. Let's have a look after just one step. So let's have a look at after our first increment, because this should just be one higher everywhere. 6594. 6594, sure. Okay, and now if we do position 1, 7, 6, 10, yeah, okay, things have not incremented as they should. That's frustrating. So let's go back and look at this a bit more. So first, the energy level of every octopus increases by 1. Then any octopus with an energy level greater than 9. Okay, we're higher, but we're not there yet. Greater than 9 flashes. This increases the energy level of all adjacent octopuses by 1. This does here. If this causes an octopus to have an energy level greater than 9, it also flashes. This process continues as long as new octopuses keep having their energy level increase beyond 9. That's why we call its increment count at that location, so it can start spiraling out. Finally, any octopus that flashed during this step has its energy level set to 0, and it used this. This feels correct to me. I'm wondering if we're overflowing a U8 somewhere, and it's wrapping around. I guess the easiest way to find... Oh, well, hold on. No, that would show up because this test runs in debug mode, right? Yeah, okay, so a wraparound like that would show, but just in case... Just set everything to U32s. No, okay, same error. So I'm going to undo that, and we'll go back to using U8s. I thought that was unlikely to be the cause. Okay, so we have to wonder, why does this go wrong? So the first step is find it. Second step goes wrong. 9 is going to increment to 10. It's then going to flash all of its neighbors, bringing this 6, 6, 5, 7, 6. Yeah, like some level of things flashing and incrementing things propagates through. Only increment if we had not yet flashed, and we set ourselves to flashed immediately so we do not double flash. Flash, we're not resetting flashed. That's the problem. Down here, we also need to reacquire flash and say target flashed is equal to false. As part of our like retreat step. Okay, now we're too high. Interesting. Could it be... No, we do all of the recursive increments before we ever hit this. Like, all increments will be resolved before we finish our flash. So this is just the fact that I think we need to separate out our flash step from our increment step. So that's fine. So we have our increment step here, which is going to increment everything. Like so. And then we have our FN reset flash step, which also has the same parameters of our so this is simply entitled reset flash. And now for this, what we do, it's very simple. All we do is we say that our target, we say if target octopus is greater than 9, target octopus is equal to 0, target, and then no matter what, we want to reset our flash state, so we say target flashed is equal to false. And then we never use reset flash, but we're going to. So here we're incrementing our entire grid, and then here we reset our flash. just on every single cell. Still wrong. Okay. We're still over flashing. That surprises me. Because we won't be back flashed because we have our target flashed. What's the state here now? Is it still wrong? It's still wrong. 7-7, only one too low. 6-4, 7-4, 6-5, 7-6, 4-4, 5-4, 5-5. Okay, it's almost right. It's just slightly wrong somewhere. Oh, and you know why? It's because this should be grid shape and not grid shape -1. It's going wrong at the edge. And that will fix it. Nope, now we way overcount, but we're now correct on this one step almost. Almost correct. We have still have 7-7 in the top left corner, but then it's 0, 7, 4, 4, 4, 5 is now, we're still 1 too low. We're still 1 too low. Why are we still 1 too low? Like we, we always increment, and then if it's greater than 9, we trigger our flash if we haven't already triggered our flash. Could it be that we need 3 steps, increment, flash, and then reset? Let's just try that. I think that there may be a reason why that needs to be a thing. Increment, flash, and then reset flash. And so in increment, all we do is we increment the octopus targeted. We don't do any of the recursive step. Then we flash, which means we don't increment. Not using target flash, which means we can remove flash from here. And we're not using counter, so we can remove counter from here. So all this does is increments the cell. Then flash doesn't need to increment the cell, but it checks if it's greater than, it still gets the values. And then it calls flash on them. But have I renamed? I've renamed flash. Let's call this flashes. There we go. And flashes. So we have increment, flash, and reset flash. And so here, what we want to do is we want to do increment. Then we want to flash. Then we want to reset flash. And increment does not care about your flashes or your count. Still too high and still wrong. In fact, more wrong now. Why? So first, the energy level of each octopus increases by 1. That is this increment step. This just does nothing but bump every octopus's energy level up by 1. Then, any octopus with an energy level greater than 9 flashes. This increases the energy level of all adjacent octopuses by 1, including octopuses that are diagonally adjacent. Check. If this causes an octopus to have an energy level greater than 9, it also flashes. If our energy level is greater than 9, then if we have not yet flashed, we flash. Finally, any octopus that flashed. And I guess we can say if target flashed, but that should be like exactly the same. Exactly the same. So why do we get 760 here? Are we fully correct on that first step? Let's check that properly, because I only read the first line. Oh, we're no longer fully correct on even that first step. Oh wait, hold on, no, we might be 637, 637. We appear to be fully correct for the first step because no flashes occur. 6589, 6. Okay, so when we just, okay, so our increment is fine. Our reset flash is dead simple. Something is going wrong in here. Okay, that brings us back down to 1,000, so now we're too low. I thought I might, I knew I was flashing, but under flashing makes more sense than over flashing. The problem was I was counting too many flashes here. So I was saying if the target, I was counting unconditionally, where they should only be counting if the target had not yet flashed. Yes. Okay, so now we're not double counting things, so now we know that our flashes are just too low, right? We are strictly under flashing. It could be to do with our grid shape not behaving properly, but I think it should. From 0 to 1 higher, but no higher than the grid shape, I guess. This will cause it to panic, I think, or to at least crash. Okay, well, yeah, I'm doing nothing if we go out of bounds, so that makes sense. But so I could probably remove this min check, because we don't if we're out of bounds we don't do anything. So target flashed. It's true. Then we want to flash on those neighbors. Oh, we're not. We want to increment them and then flash them. Increment view yx and then flash. Okay, that gets us some of our missing flashes. Are we correct here now? Nope. Wait, that's 0. Well, let's increment back up to 1 for inspection. Seven 770. 646 544. Okay, we're on this like weird off by 1 again. I wonder if the flash should propagate through other things that are flashing. Then any octopus energy level greater than 9 flashes, this increases the energy level. Yes. Okay. So I think this is weird, but the increment should happen to all adjacent, and then the flash. This is so weird. Okay, so I think the way this should work is our increment should have some of this logic. But we should say if target octopus is greater than 9. So if we are greater than 9, then increment the neighbors. Then in the flash step, if we're greater than 9, set ourselves to flashed and increase our counter. Which just means increase our counter. We now don't need to set ourselves to flash because we're now not backtracing, which means we don't need to have a flashes tracker anymore. Aha. Because in here, all we need to do, we can get rid of target flashed and get rid of target flashed. And in here we can say target octopus is greater than 9. And in fact, we can do this all in one step here. If target octopus is greater than 9, increment the counter, target octopus is equal to 0. And we can remove the reset flash pass. So now we no longer need our reset flash pass, and we no longer need a flashes tracker. And we no longer need a flashes tracker. And in here, we never refer to individual locations, so we can get rid of that. Attempt to add with overflow. Attempt to add with overflow. And we really do be overflowing. Should we go up to a U64? Okay, something going very wrong here. In fact, let's, on our increment step here, we actually have a nice little luxury we can do. So I think we're getting caught in like a little loop, right? Because we call it will back increment us. We're greater than 9. That's what's happening here. Okay. So for all of our neighbors, it's almost like we do still need flash tracking, which is really annoying. Oh, well, no, we just don't increment if we're already over 9. That's actually the trick here. We say if target octopus is less than or equal to 9, then increment it. Otherwise, who cares? Okay, now we overflow our stack because we are bouncing backward and forward and never finishing our recursion. But that shouldn't. Yes, okay, because we're greater than 9. So you visit us, then you come back to us. Is it strictly greater than 9? Okay. So the problem here, to like just illustrate, this cell flashes, which flash increments this cell, which then flashes is high enough to increment this cell, and so they just sort of back and forth. We do need to guard against that, which is that in our increment step we need to track what we visited, which means we do need our flashes, which is annoying. Yeah. I'm wondering if we can take advantage of the fact way we're scanning to only go right and down, but I don't think we can. I think we do just need to track what's flashed. So that's annoying. Let's bring back flashes. and bring it back in our variables. Okay, so now what we do is when we increment everything. If we are greater than 9, we increment all our neighbors, who might then try and increment us. So what we do is we only do this if we have not already I'm just really struggling to understand the problem definition, I think. Like what order operation should happen in. All adjacent octopuses by 1, including octopus the diagonal. This causes an octopus to have an energy level greater than 9. It also flashes. You expand out and we get a big number, then it comes back. We're still a big number. Okay, we need to just track our flashes in our increment step as well. So if we are greater than 9 and if we have not flashed, then flash and increment our neighbors. So we increment everything, including flashing and doing our neighbors. Then we reset flash, going to 0 and incrementing the count. And we can remove the flash step, and we only need increment flash and reset flash, I think. One, 2, 7, 3. And we're off by 1 again. Why? God, it's so hard to follow what could be causing that. Here we've got our 7, 7 instead of our 8, 5. Then we've got 6. It's... Is it because we're scanning? Do we need to do these operations on the whole grid at once? Like we increment the whole grid by 1, then we flash the whole grid, and then we reset flash the whole grid. Like I really don't understand what's going wrong. I think is the problem here. Like if I knew what was going on, it would make a lot more be a lot more easy to like follow what to do differently. I guess let's have a look and see what the state is after increment flash. I'm gonna do this a bit differently. What we're gonna do is we're gonna do at the start of each loop we're gonna debug our grid. Then here we're gonna debug our grid, and here well that's just for the next one. And then what we'll do is we will do std io stdin read line unwrap. So now we should have to press enter, but it's not prompting us to. Great. Whatever, let's just print all the grids and look at them. It's only 100 of them. So 659, it goes up as we would expect. And then no flashes. That's our first grid, this is our grid after we increment, and then this is our grid after we reset our flash, nothing changed. Then we have this grid after we increment, so it is the increment step that's just wrong, right? Because it's not incremented these. In fact, I mean, it has incremented these, but like this one here, let's talk about that 6, okay? In the top right. So this 9 increments up to 10, increments its neighbors to 6 and 5, and then increments its lower neighbors to 9, 6, 7. Nine, 6, 7, 9. 9. So then this is 6, this will get incremented to 7. And this 9 will go up to a 10, which will flash, bringing this up to an 8. Yet it's only gone up to a 7. Why? Let's break it up into 3 again. So still not passing, let's be clear. First we increment everything. Nothing happens. Then, in fact, let's do this slightly differently. Let's do iGrid, and then we've got, and that'll give us some way of telling where we are. So 0. Nothing happens. Now at the start of 1, they've all been incremented by 1. So this step here, they all increment, and we know which ones are going to have to flash. Then they flash. So this 10. With a flash, you need to increment before flash. Still not enough flashes, but let's figure out what's going wrong. So 0, nothing interesting happens. Then in 1, we increment. We now have some 10s in there. And then we flash. Increment ourselves, but that shouldn't matter. I mean, we can just say if y is equal to cy and x is equal to cx. Continue. So now things skip themselves when they flash. Yeah, that doesn't make a lick of difference. I didn't think it would, but it's in there now. But for the sake of being proper, so that we can see that our number is like 10 instead of 11 or whatever. There we are. So now you're 10. And so now we flash, so 10. You got to 7. 6. And then beneath the 10, Beneath the 10, it's really annoying that these don't line up. Oh, 6. Still a 6. Ooh, okay. Let me, rather than using debug, let me actually just use the print line command. That'll maybe they'll maybe look a bit nicer. Yeah, oh, okay, so much more readable. Okay, so I0 was boring, right? I1, you increment to 10, and then you should flash your neighbors. This increments to 7, this increments to 6, but the 9, 6 underneath you hasn't. Why is our row beneath not incrementing? Because we're using dot dot equals. Go up to and include y plus 1. But process exited 0. That means test is passed. Right. Oh my god, okay, sure, whatever. Okay, I feel like this has got way more going on than it should have in it, but sure. Target, release, utils, run, year 21, day 11. That should not have been as difficult as it was. Clearly my brain is not working this morning. Submit. There we go, okay, and then synchronizing. The first time all octopuses flash simultaneously is step 195. You can calculate the exact moments an octopus will all flash simultaneously. You should be able to calculate what is the first step during which all octopuses flash. Okay, nice and easy. All we need to do is do the exact same thing in task 1 in task 2 as task 1. And then in here, all we need to do is say for I in 0 forever. And then we're going to say after we flash before we reset, if flashes dot iter dot all, if everything is flashing, then return I. Return OK I, and you are a U size. Let's test task 2. So test task 2 should be 195. $194. Okay, we have an off by 1 error, sure. Start at 1. Yep. It's always nice that even though part 1 took me way too long, the way I've built it means that part 2 was pretty much instant. 515 is what I'm going to claim. That's the right answer. Okay, let's clean this code up a bit, because this code is awful. Right. Let's just like work through all of these things. Remove unused import. Yep. We don't use CY or CX in here, so we can just call it target. We don't use CY or CX in here, so we can just call it target. We don't use I, so we can call it underscore. Okay. And hopefully Clippy doesn't have much to shout about. Clippy always has things to shout about. Cargo Clippy fix, and then it's going to tell me to do cargo Clippy allow stage dirty. Allow dirty. Fix. Thank you, Clippy. That's the only one with problems, but thank you for checking all of them. Go Clippy. Okay, let's just cargo format as well. Status dot commit add 2021 day 10. All right, thank you very much for watching.